Good day everyone, my name is Anton. Today I'm joined with Alex and Pablo. We are members of Monash HPR Rocketry. We're an undergraduate team from Monash University in Melbourne, Australia. Today we'll be presenting about small design changes with a disproportionate effect on trajectory, plus also how we've used our simulation software to analyse these effects. With the unreliable access to flight testing, the limitations in accuracy and the features of open source simulators, and the difficulty in analysing design trade-offs, it is important to develop a simulation tool that allows us to understand these designs and effects. For this presentation today, we'll start by discussing our trajectory simulator, Saturn. We'll then move on to different trade-off studies that allowed us to understand better performance, specifically with regards to apogee. Also looking at the sensitivity of our small design changes. Finally, we'll look at the unanticipated effects of small design changes through the case study of standoff railway guides, through the that we've done for our competition rocket Ether. I'll now be talking about the first part of our presentation, introducing Saturn. Saturn is our custom, in-house built 6 degree of freedom rigid body simulator, which we made in the language Saturn, which is a combination of Python and C. This was implemented as a solution to the 3 problems previously stated in this presentation. With high-fidelity simulations of trajectory before flight, we are able to gain a little bit more independence of the need for launchers to be able to assess our designs. With a high accuracy and flexibility, that means we're able to perform more detailed trade studies for our designs. With the extensive nature, that means we're able to capture more detailed physical models of the rocket. Looking at the plot on the screen, this is one of many outputs that we're able to get through Saturn. This specific plot is showing us our rocket's Ether, its flight path, going from ignition up until apogee. An important part of Saturn is the visualization tool. So instead of just having arrays of data and plots, we're able to turn our data into visualized representations. We use computational fluid dynamics in order to create an aerodynamic database. These inputs are determined by 3 dimensions made up of Mach number, roll angle, and angle of attack. The permutations in the table are calculated from the known bounds of the flight. For our roll angle, we specifically use 0 and 45 degrees. As we're able to solve for one quadrant, we're able to get the aerodynamic coefficients for all other roll angles by assuming tetragonal symmetry about the surface. This greatly increases the efficiency of data acquisition as we significantly reduce computational time. We also use Monte Carlos, which are a numerical analysis technique in which we stochastically vary a wide range of parameters in order to make a large varied set of simulations. This allows us to account for uncertainties that may occur during launch. For example, say we have higher wind speeds than that of the predicted weather, we're able to account for that, as well as say our rocket is experiencing greater drag forces than that of simulated data. The plot is also showing all the randomly generated trajectories, where the grey lines represent an off-nominal case and the blue line represents the nominal case. Off-nominal flights are a flight with a random attribute to a range of independent variables. This can include mass, environmental conditions, aerodynamic coefficients, and more. In the plot, we have completed 10 different iterations in order to clearly identify each off-nominal case. But for context, in a usual investigation, we'll complete up to 200 iterations in order to obtain a confidence bounds. It's very important to verify accuracy for all software. We achieve this by comparing our flight data to that of Saturn data. From the plot, we're looking at error percentage, error and apogee percentage of OpenRocket and also Saturn. Saturn achieves a consistent and accurate result, which gives us a lot of confidence for our flights. More the fact that it's able to do this over a large range of rocket sizes, mark regimes, and altitudes. Looking at our competition rocket Ether, we're able to get confident results as we achieve apogee errors of roughly 3%. If we attune our results for wind data taken on the day of flight, we're able to get results that is less than 1%. I'll now be passing on to Pablo to discuss the trade-off studies.
So a big part of our goal in this design cycle was to use Saturn as a design tool so that we could use designs and put them through our simulator and really understand how trade-offs affect our design decisions. So, starting with the biggest design trade-off that we analysed was the mass aerodynamic trade-off. In the plot, we can see contours of constant apogee. The grey line is achieving the target apogee. The red lines are if we undershoot apogee, and the blue lines are if we overshoot apogee. From this plot, we can see that small changes in aerodynamic forces dominate our apogee error. Indeed, a 1 kilogram extra mass is equivalent to only 4% error in our drag estimate, which is a very small percentage of our drag estimate error. So, tying this into how we use Saturn as a design tool and our design cycle, we have come up with 3 different design decisions. We have committal design decisions, which are decisions made at the start of the design cycle. These are decisions which are not to be changed and which specify the tolerances with which we hold the team accountable to. Secondly, we have adjustable design decisions. These are decisions which are medium to long term, which can be changed if the rocket is not performing how it is expected. These are decisions which can be triggered if required in order to make large changes to the trajectory, considering that our design is not going to plan. Finally, we have tuning parameters which we use for on-the-day performance changes. These are used for weather conditions which may be affected on the day and thus are calculated on the day. Looking at one of the first trade-offs is the fin thickness analysis. This is a committal design decision, and what we found is we are very sensitive to our fin thickness. A mere 1 millimetre difference in fin thickness changes our drag by approximately 4%. As we can recall, this is equivalent to a whole kilogram of extra mass, or 600 feet in lost apogee. This is a small change which has drastically affected our apogee. Moving on to wedge angle, another committal design decision, we can show that changing the wedge angle from its nominal 32 degrees to either 21 or 46 degrees changes our drag coefficient by around 10%, which is equivalent to 2.5 kilos in extra mass in terms of lost apogee. Therefore, it is another variable which we would like to hold the team accountable to in early design cycle. Moving on to surface roughness, which is an adjustable design decision, this is based mainly on theory at the moment. What we've found is that an optimum spray painted surface gives a roughness of around 5 microns, whereas a regular paint surface gives a roughness of 60 micron. This is equivalent to a loss in apogee of 3,500 feet. Currently, the team aims to hit its apogee and achieve the maximum performance from the rocket. Therefore, we strive to achieve the optimum spray painted surface, sanding the rocket down to 2000 grit and ensuring that the spray paint is applied properly. Another adjustable design decision is the forward tube length. With Project Ether, there were concerns that we may not reach the targeted apogee of 30,000 feet. Therefore, we had 2 backup plans in case we needed to make an adjustable design decision. One of them was reducing the forward tube length by 150 millimeters. This would increase our apogee by 1,300 feet. If we needed to go further, we could change it by 300 millimeters and then increase our apogee by 1,700 feet if required. Summing these all together, we can estimate our control authority for our Project Ether. Firstly, the punishment for missing design tolerances can be up to negative 4,000 feet. That is a loss of 4,000 feet in apogee. Therefore, we strive to hold the rest of the team accountable to design decisions they have agreed to. In terms of adjustable decisions, we have an estimated 5,000 feet of leeway if the rocket requires more performance or less performance. Finally, on the day, we can tune to around 1,500 feet, depending on weather conditions. To summarise this in terms of competition performance, we can say that being 1 kilogram over the mass budget, or 4% error in drag, means that we will miss apogee by 600 feet and lose 24 competition points. To put that into perspective, 24 competition points is around 10% of the technical report. Given that a technical report requires around 1,000 person hours, this 1 kilogram in extra mass is around 100 person hours worth of work. Therefore, we like to hold the team accountable to design decisions and make the team think about every kilo and every aerodynamic advantage that we can get, and to quote this 100 person hour as a metric to hold the team accountable. To summarise, we have found that drag is generally a greater performance concern than mass. We have also found that very small aerodynamic changes can result in large changes in apogee. Finally, the fact that the team is efficient and has refined processes in its simulations and CFD, we can produce these alongside our design changes and design cycle, allowing us to be quick and to assess designs in a rapid manner. I'll now pass on to Alex.
Thanks, Pablo. So in addition to analysing the extreme sensitivity of apogee to different design parameters, the team has investigated how small design changes can have unanticipated effects on your entire vehicle trajectory, and we've highlighted how important modelling and simulation are to de-risking your vehicle before flight. To analyse this, we'll look at a case study of Monash HPR's 30,000-foot entry, Project Ether. As you can see on the right, Ether has a 6-inch forward tube which transitions down to a minimum diameter 4-inch rear tube. As a result, we require relatively long launch lugs to retain the vehicle during liftoff. Unfortunately, due to rule changes for the Spaceport America Cup, the original plan to use flyaway rail guides was no longer allowed due to mass and size restrictions. On a relatively short time cycle, the team had to investigate different options to retain the vehicle on the launch rail. We investigated several different options, including angled launch lugs, retractable launch lugs, and Steindorf rail guides. However, due to the limited available test opportunities and the extremely short design cycle, the team opted to use standoff rail guides. They're relatively simple compared to the other options and were easy to manufacture. Overall, the expected effect of the addition of standoff rail guides was relatively negligible. We knew that they would have an effect on apogee, but we considered this a necessary design constraint, and we'd make up the performance through the adjustable design decisions that Pablo mentioned. However, what we found upon analysing these were that they had an extremely more far-reaching effects on our entire trajectory than we could have expected. The primary area of concern was the asymmetric aerodynamic forces acting on the vehicle. On the left, you can see a contour plot taken from CFD at a Mach number of 1.4 and 0 angle of attack. We're taking a static pressure contour on the rear launch lug, and as you can see in the top right quadrant, there's a large high pressure region forming due to shockwave formation over the lugs. Due to the distance from the centre of gravity and the relatively high magnitude of the high pressure region, this gives rise to a strong perturbing moment during supersonic flight, even during axial flow. On the right, you can see what this axial flow moment coefficient evolves as a function of Mach number. At low subsonic speeds, we have a relatively low magnitude nose-down pitching moment, but as we accelerate through supersonic flight, this dramatically increases in magnitude and switches sign. So throughout our entire supersonic flight, we have this really strong perturbing moment, taking us away from nominal. Having analysed this, having analysed this, it was crucial that the team was able to implement this in Saturn, our simulation tool, and understand how this affected our vehicle's trajectory. The aim with our model was to implement something simple and that did not significantly increase the amount of CFD we had to do while maintaining an acceptable level of accuracy. As such, the driving assumption behind our model was that the moment coefficients from the launch lugs was independent of angle of attack and roll. As such, we can make the decomposition shown below, where we have a symmetric part of our moment coefficients, which is a function of Mach number, angle of attack, and roll, and a static trim part, which is caused by the lugs, and only a function of Mach number. These assumptions do have several impacts. So firstly, we slightly overpredict our moments at an angle of attack, and we don't take into account flow being blocked by the airframe. However, our multicolor analysis has shown that the angle of attack during flight maintains below 1 and 2 degrees throughout our entire flight and all expected operating regimes, so these effects are relatively negligible. Having implemented this in Saturn, we found that the effects were both far more wide-reaching and higher in magnitude than we initially expected. Firstly, we have a dramatic increase in our axial CD between 4 and 12% as a function of Mach number. So at our max Mach number, this is equivalent to an additional mass of 2.5 kilos. Separate to the increase in axial drag, we also have a distinct pitch over event, which you can see on the right. At around 3 to 5 seconds, when we reach supersonic flight, the perturbing moment from the lugs causes us to deviate from what our nominal no railguide trajectory is, and this causes an additional loss of apogee. Combined, these two effects give us around a 2,500 foot apogee loss performance, which is a really significant hit to competition performance. In this visualization here, we're showing two different simulations. One is with railguides and the second is without, and we're tracking the rocket with railguides. As you can see, although they have a relatively similar trajectory at the start of flight, they quickly deviate when they reach supersonic flight. Additionally, in the bottom left, you can see the angular rates of the two flights compared, and the flight with railguides has significantly higher angular rates, and hence significantly higher angular rates than the case without railguides. Despite these increased angular rates, the vehicle maintains stability throughout its entire flight, and through Monte Carlos, we've shown that this is consistent across all our expected operating regimes. As such, the team is confident that although the railguides have a significant effect on our trajectory, they don't pose a significant risk to the vehicle's stability. A more critical flight risk is the increased aerodynamic loading that we have on the vehicle. Without railguides, when we're during high supersonic flight, there's no perturbing moment that gives rise to an angle of attack. As such, the lateral aerodynamic loads on the vehicle are relatively low. However, once we add railguides, there is that perturbing moment which gives rise to an angle of attack during supersonic flight. You can see this really clearly in the plot to the left. So between around 5 and 10 seconds, when we're supersonic, we maintain a consistent angle of attack between 1 and 2 degrees. Here, we've included our results from Monte Carlo analysis to understand what our worst case scenario might be. This increased angle of attack then corresponds to, on the right, an increased lateral aerodynamic forces. From my Monte Carlos, we found that in the worst case scenario, this results in a 10 times increase in our aerodynamic forces, which is not something that we expected before implementing the railguides. With this increased loading, we were really pushing the factor of safety limits we had for bending on the vehicle that we generated from structural simulations. As such, we revisited those simulations with the updated loading, and we found that we were still within the factor of safety limits, but with relatively little margin. As such, we endeavoured to increase our margin and close out the risk through two other ways. So firstly, we made several design changes. We increased the thickness of the rear tube where bending was highest by 50%, and we changed our resin system to a system that required a post-skewer, which significantly increased its strength. Additionally, we've conducted one shakedown flight with the airframe on M3400 motor, which took us to Mach 1.0. So although this isn't necessarily the same as the expected loading on our 3400 competition motor, it gives us some level of confidence that in the soundness of Ether's airframe. To sum up, we've covered 3 key points in today's presentation. Firstly, our apogee is extremely sensitive to a wide range of different design parameters. Secondly, small changes can disproportionately affect your trajectory in many different ways, and it's important to consider more than just apogee. Finally, the underlying theme of this presentation is that accurate simulations are crucial. Through the development of a detailed and versatile simulation tool, the team has the capability to accurately quantify and understand the effect of different small design changes. By being able to conduct detailed design trade-off studies rapidly and model non-standard effects such as railguides, the team is able to de-risk their rocket and optimize competition performance. Thanks very much, and we're happy to take any questions.